Okay, cool. So let's see. Uh, Welcome to hydrogeology, GEO 420. And I thought I'd just start the day off by looking at the schedule. Okay, so we're here on the 18th. Today we're going to talk about storage and aquifers and aquatards. We'll get into geology and regional groundwater flow. I printed something out today and I forgot it, so that sucks. On Tuesday, and then Thursday we'll have the exam. All right, so just a reminder, Thursday is the exam. The exam will be through what we cover today. Yeah, so the exam will be through essentially this Toth paper that we're going to read. So what I had printed out and what I forgot to give you is a reading summary guide. So what I want you guys to do is read Toth before class on the 23rd, this paper, and do a little summary. I'll post that on Moodle. And it's really basic. It's like, what's the paper about? What did they do? Things like that. I want you to read it before class. And so here's the deal. If I was to grade the three most important hydrogeology papers, Toth is number 2. All right. So this is an old paper, but it's a really important paper. All right. So read it. We'll discuss it, and that'll be sort of the last bit of stuff that we cover before the exam. So yeah, that's the main thing I wanted to hit on the schedule. Exam. Yeah. And it wasn't there? I just pressed on it. It says like reading assignment, and then it took me to like the listener link instead of like a that paper. Okay, that's my fault. So we should I will make sure that ENUMARK and Toth are available. They should be up, but well, I thought I had them up, but what I think I have up isn't always the case. So I will make sure I put them up right after class. And if you can't get to them right, like if by noon you can't get to those papers, please email me and I'll figure out what I'm doing wrong. We'll do a bit of the discussion of ENUMARK next Tuesday as well, because it does have something to do with what we're going to talk about today. Okay. Any other questions? Thursday exam. I will have an exam. I'll get the equation sheet together for you guys. I'll give it to you guys on Tuesday. So you don't have to memorize the equations. The equations will be on an equation sheet. I give them out Tuesday. None of the equations will be things you haven't seen. Well, let me put it this way. There will be only equations that you've seen so far. You may not need them all on the test. But one thing is to make sure that you have time to go through it and be like, well, I don't understand what this symbol is right here. I try to keep the notation consistent, but it might look a little different on the font. Maybe, maybe I didn't keep the notation consistent. So Tuesday through Thursday is a time for you to look at that equation sheet and make sure that you understand it and that you can ask me questions. Bottom line, we'll have some time Tuesday to talk about the test, but you know, the bottom line is the main thing that the test is going to be on is stuff that you've done in your homework. All right. So I'm not going to ask you any curveball questions. It should be similar types of questions to what you've done in the homework. Okay. I guess something that we need to just start putting on the radar. This is as much for me as for you. Field trip in the beginning of April. All right. I'll start thinking about planning that. It'll be a Saturday. We'll go out to Lolo. Hopefully make some groundwater measurements. So just something to sort of put on the radar. It's a long ways out, but definitely needs to be on my radar because I got to start planning it. Okay. Schedule. Ooh, what's this? Nothing that we're working on. Just a little bit of stochastic hydrology. Should we get into that today? Yeah, they're horrible. Okay. All right. So we're gonna go almost in the opposite direction from stochastic hydrology today, and we're gonna start talking about just some basic terminology, definitions, and of aquifer systems, and then we're going to get into talking about storage, which is always a mind bender. So, but no heavy math. Okay, so all right, so as we start to talk about geology and how it affects groundwater systems, we need to start getting some more vocab. And so I thought we'd just start off by making a little drawing here of a gently rolling hill slope. All right, this is the land surface. And down here in the valley, we've got some kind of stream, right? And then let's start looking at the subsurface. So let's have a few layers here. So let's have a layer down here of shale. And let's have the top layer up here be sand dunes. So my PhD advisor has currently got this big research program in the sand hills in Kansas or Nebraska, sorry. And this is literally what it looks like. It's sand dunes with rivers in between the sand dunes. And if you're a hydrogeologist, it makes everything super simple. He's cheating. All right. And then beneath that, we'll have another sandstone. And we'll finish our sequence with another shale. Okay, so this will just, this is loose sediments, sandstone or sand. This is a shale. Sandstone and a shale. And so the stream system here will generally be connected to a water table. All right. And one rule that we have and that will become important for the Toth paper is that in general, the water table is a subdued replica of topography. All right. That means where there's hills, the water table generally rises. Where there's valleys, the water table generally falls. It doesn't rise as fast or fall as fast as the topography, but it generally follows the same shape. Okay, so where there's mountains, the water table is higher than in the valleys. All right. And for virtually all natural settings, if you've got surface water perennially, all right, like a river that flows year round or a lake that's there year round, it is connected to a groundwater table. It's basically impossible to have surface water year round without it being connected to a water table, all right, to the groundwater system. So anytime you have surface water at the land, like when you walk and you see the river or you see a pond, think of that as, oh, look, there's the water table at that point. All right. And if I was to drill a well immediately adjacent to that pond, the water table would be basically the height of the pond or the river. A little bit higher or a little bit lower, as we'll talk about later, but almost always. All right. Okay. So um, this is the water table connected to the surface water. All right. So the bottom line is, as hydrogeologists, we break the world up into essentially two kinds of units. We have aquifers. So this might be an aquifer. All right. And then the other type of unit we have are they either get called confining units or aquitards. And it depends a little bit on which country you're in. But confining unit or aquitard. And we're going to define these rigorously, well, kind of rigorously in a second. But the bottom line is an aquifer is something that will yield a usable amount of water. All right. And in a confining unit or aquitard will not. So in this drawing, I've drawn two aquifers and two confining units. All right, now there are, so we break these things up based upon hydraulic conductivity. So an aquifer essentially has high enough hydraulic conductivity that I can pump and the water will flow. All right. A confining unit has low hydraulic conductivity. And so if I put a well there, no water will come out of it. All right, so basically the world to a hydrogeologist is either an aquifer, it has a high enough hydraulic conductivity that can pump water out of it, or it's a confining unit, won't yield water if I pump. Now, there's no hard cutoff on what's a usable amount of water. All right, so this is one thing that we're just going to have to deal with when we talk about aquifers. Sometimes something's an aquifer because we can pump it, it yields enough water, say, for a house to use, but it wouldn't yield enough water for the city of Missoula to use, right? So these things are a little bit relative. All right. Now, some important distinctions. So this aquifer, this top aquifer, the top of the aquifer here is the water table. So the upper surface of this aquifer is the water table. So this aquifer has a thickness that is determined by the water table. And that kind of aquifer is called an unconfined aquifer. All right, there's no confining unit at the top. The top of this aquifer is the water table. So let's go down here and just write a few definitions. So an aquifer will yield a usable amount of water. All right. An unconfined aquifer has the water table as its upper boundary. Okay. So if I was to come here and drill a well, all right, and I screened it right here. All right, that's my screen. So here's the water table. What would the water level inside this well rise to, you think? What elevation? All right, so if I drilled a well in this unconfined aquifer, it would probably rise. We'll talk about this later. It might actually, given this screen location, not rise exactly to the water table, but it would be close. So it would rise to the height of the water table. So I'd have water in my well up to the height of the water table. Okay, unconfined aquifer. Water table is its upper boundary. This upper boundary or the water table also gets called the phreatic surface. And so another term you'll hear in the literature for unconfined aquifers are phreatic aquifers. They have the phreatic surface as their upper boundary. It's totally the same thing. Phreatic aquifer and unconfined aquifer are the same thing. They have the water table as their upper boundary. They're always near the surface of the, so these are always the shallowest aquifers, all right? They have the water table as their upper boundary. All right. Now, this aquifer down here has a thickness between two confining units. Its upper boundary is not the water table, it is the confining unit. All right. And this gets called a confined aquifer. So in a confined aquifer, we have a confining unit as the upper boundary of the aquifer. And let's go ahead and define, I haven't defined confining unit. So confining unit has limited to no groundwater flow. All right, this is just a formation that has low enough hydraulic conductivity that it doesn't allow much or if any groundwater flow. All right. Okay, so if I drilled a well now here and it's cased all the way down until I get into this lower aquifer, and then it's screened in this lower aquifer. All right, so this is case, no water can get in from the unconfined aquifer. It can only get in through my confined aquifer. What does the water level rise to in this well? How high do you think the water level rises in this well? Okay, above the water table. Okay, so we've got, it could be up here. Let's draw this, draw it in a different color. So Jenna says, well, it's going to be above the confining unit, but maybe not above the water table. Tessa says above the water table. Could be above the land surface. So the bottom line is all of these are right. We don't know. It could be any one of these. The water level inside a well in a confining unit has nothing to do with the water table. It can be higher, it can be lower. So the water level does not equal the, let's say the, in a well. I gotta. How about this? The head. The head. We have terminology for this. The head in a confining unit or confined aquifer is not equal to the water table. Now, I think Jenna said an important thing. If my water level inside this well was below the confining unit, what would that imply? Yeah, there's an unsaturated zone above. So if this well was below the confining unit, then there's an unsaturated zone here. And then the confining unit is not the top of my aquifer. All right, so for a confined aquifer, the head inside the aquifer has to be above the confining unit. That's the definition. So the head in a confined aquifer has to be greater than confining unit. It'd be an unconfined. Anytime the unsaturated zone is the upper boundary of our aquifer, then we have an unconfined aquifer. So let's talk about, there's two terms there that we can talk about though. All right, so the bottom line is, if I come in here and I measure the head in this confined aquifer, it has to be above the elevation of the confining unit. So there's some more specifics here. So if the water level's above the land surface, all right, so if the water level's up here, this is called an artesian aquifer. All right, and artesian means the well would flow at the land surface. All right, so here's an important thing. If you have an artesian aquifer, it has to be a confined aquifer. So if we were in the case where this had an unsaturated zone, and we could, create an unsaturated zone by pumping enough out of this water that we created an unsaturated zone. I'll make it extend here. So if this was actually an unconfined aquifer here, all right, then if we have an unconfined aquifer over another unconfined aquifer, this aquifer gets a special name. It's called a perched aquifer. So an unconfined on top of another unconfined aquifer. is a perched aquifer. All right, and in order to have a perched aquifer, you've got to have a low permeability layer, and you can have a unconfined aquifer sitting on top of that low permeability layer, and then you have to have another low permeability layer and have another unconfined aquifer sitting below it. They're rare, but they do occur. All right, so the main takeaways here are we break the world up into aquifers and confining units, all right? And that there are two major types of aquifers, unconfined and confined, all right? And the water table only matters for the unconfined aquifer. In an unconfined aquifer, the water table doesn't really mean much to us. All right. As we go on and develop the equations of groundwater flow and think about how we model or calculate groundwater flow, it matters a lot what kind of aquifer we're in. All right. So being able to distinguish between these types of aquifers is really important. All right. And the bottom line is if the confining unit, if the water level inside our aquifer is above a confining unit, it's a confined aquifer. If the unsaturated zone creates the top of the aquifer, it's an unconfined aquifer. There's no confining unit that's limiting the top of our aquifer. Okay, so as just quickly, let's get rid of this perched aquifer stuff and just consider this case where we had our unconfined and our confined aquifer here. If my water level was, if I drilled this well and the water level rose to here, which direction in general would fluid flow be across, so vertically across this shale? So Jenna's got an answer, but I want someone else. So which direction would water move between these two aquifers? Okay, so 2 votes for down. Why? Okay. Pressure is not the right term though. Pressure is part of it. You're not wrong to say pressure, but you're not right. Head. All right. Water flows according to total energy, not just pressure, right? So the head in this aquifer is up here. The head in this aquifer is down here. The head is higher in the upper aquifer than the lower aquifer, so water would tend to move this way if this was the head measurement. Okay, let's consider this one. What's the case if we measured the head here? What's the relationship between the fluid flow in this aquifer and this aquifer? So now my head I measured in my confined aquifer is up here. Which way does it go now? Autumn, what do you think? Up. All right. My head here is now higher than my head here. And so fluid flow would move this way, right? So water always moves from high head to low head. All right. That's the easy, great thing about groundwater head. It's an easy way for us to measure the total energy. And from these measurements, we could tell whether water would tend to flow from this one into this one or from this one into this one. And the bottom line is a confined aquifer could be either. It can be gaining from the unconfined aquifer, or it can be overpressurized and want to move water up into the unconfined aquifer. Those are both common occurrences. Okay. So this is our basic anatomy of groundwater systems. As we go on, we're going to talk about unconfined aquifers. We're going to talk about confined aquifers. We're going to talk about confining units. All right. Now, let's start to think about, as I said, the physics of the groundwater flow, the amount of water that we get out of these aquifers is very different. And so let's start by considering one of the first ways these aquifers are very different. All right. And that is in the storage. So we're going to introduce a new parameter or variable that describes aquifers, and that is storage. And storage in generic terms, storage is basically some measurement of how much water we're going to get out of the aquifer per unit drop in head. All right. So if I drop the head by a meter in my aquifer, how much water did I get in order to drop the head? So generically, it's a measure of the volume. And we'll write this out in math here, of water released in order released for a unit drop in head. And when I say unit, I mean whatever unit we're in. If it's a foot, it's a foot, 1 foot. If we're talking about meters, it's 1 meter. All right. So per unit drop in head. So we'll start off with what's conceptually perhaps the most difficult, and that is in a confined aquifer. So I'm going to consider a column here of our confined aquifer. All right, and this top level here, this is the confining unit boundary on the top, and here's the confining unit boundary on the bottom. This is the confining unit. And, this is my sandstone. All right. So this thing, it's a confined aquifer, so it's full. It's full of water, right? And in fact, if I had a well installed in here, the water level would have to be above my confining unit boundary, right? All right, so let's say I magically installed a little drain here, all right? And I was able to just pour water out of this thing and fill some vessel. All right, so I filled it. I filled this vessel with water. And I did that such that as I drained out of here, I had to drop. As I drained out of here, I reduced the pressure or the amount of water in here, and I dropped my water level by whatever, 1 meter here. All right, so I drained the water, I dropped the water level, and I measure this volume of water. So this right here is my unit decrease in head. All right. And this is the volume of water released. Okay, so we're going to define a term here. It's called the store activity. And it gets the big S symbol. And big S is the volume of water released from my aquifer per unit area of the aquifer. So this area here, this is the area of the top here of my column. So this is the area of my column A, the cross-sectional area of my column. All right. Per unit area per unit drop in head. So let's call that unit drop delta H. All right, so storativity is this volume of water that we got times the area, cross-sectional area, or divided by the cross-sectional area of our column times the unit decrease in head. All right, what are the units of this? What's the units of volume? Length cubed. What's the units of area? What's the units of a change in height? Length. Length cubed over length cubed. Storativity is unitless. Okay. So this is storativity. All right. The volume of water released per unit drop in head times the area of cross-sectional area. All right. Now, I'm gonna define one other term here. And I'm gonna say, hey, my aquifer's got this thickness. All right, B. So B is the thickness of my aquifer. So we're gonna define specific storage, SS. And specific storage is the storativity divided by the thickness. All right, and I can write this out. It's the volume of water that we release divided by the area times the change in height. So this is just the definition of storativity and divided by the thickness. What are the units of specific storage? One over length. We got length cubed here, length squared, length, length. So we got length to the fourth on the bottom and length cubed on the top. So this ends up being 1 over length. All right, these two numbers are how we parameterize how much water we get at, that is available for us from an aquifer. All right. So when, foreshadowing, when we turn a pump on, we're going to drop the water level inside a aquifer. All right. And what storage tells us is how much water can we pull out for each meter that we drop the head level or whatever unit we're in. All right. How much water is available for us to take out of this aquifer? All right. So let's think about the differences in these storage and where the storage comes from a confined aquifer and an unconfined aquifer. So we're going to consider a confined aquifer first. Because it's the most mind-bending one to consider. All right, so let's go up here and look at our column here. All right, so we're in a confined aquifer. The water level inside our well is above the confining unit. All right, so we're fully saturated. And I drained this water out of here. Where did the water come from? I guess my question here is, I didn't drain any pore space. Like when you probably think of releasing water out of an aquifer, you say, oh, I drained pore space. I took pore space and I drained it, and that's where the water came from. Where did this water come from? How did I release water out of this aquifer, but it's still full of water? So it's a conundrum. I released water, but it's still full of water. How do you do that? Okay, so I could potentially be draining water somewhere else. What if I tell you we're not doing that because then I'd be in an unconfined aquifer. So how do I release water, but it's still full of water? Oh, I could collapse the thickness of the aquifer a bit, right? So a good analogy here is, let's say I've got a balloon that I blew up, all right, and I'm pinched the end. I can let some air out of that balloon and then close it. That balloon's still full of air. It's just not as, it just didn't have, I released some pressure, right? So when I release water from a confined aquifer, it can only come from releasing the pressure. When I do that, my liquid, actually my water, will expand. When I reduce the pressure, the fluid pressure, my water can expand a bit, and my porous media will collapse a bit. So the places I get water from, when I pump water out of a confined aquifer, it's coming from expansion of the water and collapse of the porous media. So let's look at that. Let's do some drawing here and think about it. So here's our, I'm going to zoom in on a little square of our porous media. So let's zoom in on a little square here, all right, of our porous media in our confined aquifer. And we're going to be zoomed way in. So I've got a few sand grains here. And they would be touching, but for simplicity, I'm going to keep them from touching right now. All right, so let's think about the forces acting on these grains. All right, so each one of these grains is getting pulled down by gravity, right? The force of gravity is pulling these grains towards the center of the earth. All right. But the fluid pressure, I've got water in here, and so fluid pressure is pushing on them. All right, so the fluid pressure is acting here, pushing these grains apart. So this is the fluid pressure. All right. So when I release pressure inside so at some, before we started releasing water, the fluid pressure was high and it's pushing these grains apart. When I start to pump water, I lower that fluid pressure, I change the force balance, and the gravity starts to win, and my grains collapse. So as we pump, water out of an aquifer, we reduce our fluid pressure, P, and the grains compact, or the distance, the grains move together. grains smush together. We're going to use so this is compaction of the porous media. All right, the other thing that happens is, so what pressure means is that we're forcing the water closer and closer together. So at higher and higher pressure, these molecules are packed together really, really tight. All right. As we release pressure inside the fluid will expand. There's less molecules being shoved together. All right. And the fluid can expand. So as we reduce, the second thing that happens is that as we reduce P, the fluid, here water, expands. All right. So when we pump water out of a confined aquifer, the place that water came from, the reason why we were able to get water out but keep the aquifer full was because we smushed the porous media together, we compacted the porous media, and we expanded the fluid. Those are the sources of storage in a confined aquifer. They're the only sort, if as long as our aquifer remains confined, they're the only sources of water when we pump a confined aquifer. Well, they're the sources of storage. We can have flow from other points, but that's a different process. All right. So those are the only sources of storage: compaction of porous media, expansion of the fluid. All right. So we can write for a confined aquifer an equation for the specific storage. The specific storage is equal to rho water G beta sub P. We'll talk about that in a second. And rho water G N for porosity, beta sub water. All right. So all of these are defined. This is density of water, gravity, gravity. N is porosity, but beta sub P is the compressibility of the porous media. All right. And it has units of meters squared per Newton. All right. It's something to do with how much I compress this porous media per unit force. All right. And beta sub water, you could probably guess, is the compressibility of water. All right, and that's in meters squared per Newton. All right, so if we go back up to our equation, this is process one. All right, this term here is the compression of our porous media. And this term here is process two, the expansion of water. Okay, let's take a 5-minute break. Stop recording here. And okay, so now let's think about an unconfined aquifer. And all right, so in an unconfined aquifer, I'll draw my column here again. Here, in an unconfined aquifer, the water table is the top of my aquifer. So I'm only saturated in my aquifer beneath the water table. All right, in this aquifer, if I drain water out here and I drop the head, all right, if I drop the head in an unconfined aquifer, the only way I can do that is by dropping the water table level, right? So a unit drop in head in an unconfined aquifer implies that the water table drops ahead. All right. So in an unconfined aquifer, I drain pore space when I drop the head, because I've moved the saturation elevation by that drop in head. I have to drain pore space. So in an unconfined aquifer, I still, when I drop the head, I'm still reducing the pressure, the fluid pressure. Okay, and so I still release water from those same unconfined aquifer, or sorry, confined aquifer mechanisms. I still reduce the pressure, so I still compact the sediments and I still expand the water, but I also now have drainage of pores. So storage comes from compaction of porous media, expansion of water, all right? And these were our confined. These were the same mechanisms that a confined aquifer has. But now we also add drainage of pore space. All right, we're physically draining these pores. So let's just consider this volume of water right here that we drained. Let's just think about it. So that went into our beaker here. All right, so this is our volume of water that was drained. All right, and let's calculate the storativity here. So remember, storativity was the volume of water drained all right, times the area times delta H, right? Remember that? Now, let's think about, in this case, I've drained this, so the pore space volume that I drained is this, right? So here I've drained this pore space. So we could also think about this being equal to the volume of water that I released over the volume of pore space that I drained, or the volume of the porous media that I drained. So we made measurements of this guy. Do you remember what it's called? The volume of water we could drain per volume of porous media. Well, no, volumetric water content was what was left after we did it. Yeah, specific yield. All right, so this is the specific yield. So the volume of water released from the drainage, that's the specific yield. So let's write storativity, total storativity for an unconfined aquifer. S is equal to the specific yield, and this is for drainage of the pore space, plus those same processes that occurred for an unconfined aquifer. So we have rho water G beta sub P plus, and I got to put a bracket here, rho water G N beta sub water. And this is times B, the thickness of the aquifer. So this is we'll talk about why that B is there in just a sec. This is process 1, drainage of the pore space, or sorry, this is process 3 up there. Drainage of the pore space. This is process 1, compressing the porous media. And this is process 2, expansion of the fluid. All right, and then I have this beta here. Well, the reason why we have this beta is this guy. This whole term is the specific storage. And recall that in order that specific storage was equal to the storativity divided by the thickness. So in order to turn this into a storativity, it's equal SS times B. So this is SS times B. So S is equal to SY plus SS times B. If I use these two relationships. Okay, so the bottom line is storage in an unconfined aquifer comes from 3 mechanisms, all right? 3 is bigger than 2. So which one has more storage available? Which kind of aquifer? Yeah, it's got 3 different ways we can release water. We get it from compression of the porous media, we get it from expansion of the water, and we get to drain pore space. All right. In a confined aquifer, it's just the compression of the porous media and the expansion of the water. That's it. Okay, so let's do some calculations and let's see just how much greater this puppy can be. All right, so let's say we've got we'll start off first with just the confined aquifer calculation. And this is 100 meters by 100 meters of sand, all right? I'm going to give you some stuff you need. So compressibility of the porous media is 1 times 10 to the minus 8 meters squared per Newton. Compressibility of the water is 4.8 times 10 to the minus 10th meters squared per Newton. All right, and sand, give me a porosity. What should we use? Finch likes 0.3. Let's go with 0.3. All right. If I drop, so if we dropped the head 3 meters, in a confined aquifer, how much water was released from storage? All right, so first calculation is confined aquifer. Oh, and you're going to need a thickness. We'll make this 10 meters. This is a beta. I don't know if that's clear or not. All right. So first of all, we'll do it. We'll give an example. So given, all right, what do we need? We need beta P, that was 1 times 10 to the minus 8 meters squared per Newton. Beta W, 4.8 times 10 to the minus 10 meters squared per Newton. N was 0.3. B is 10 meters. And A is 1 times 10 to the 4th meters squared. You have anything else? I think that's it. All right. What equations did you use? SS is equal to rho water G BP plus NBW. I just rearranged it a little bit. Is that okay with everybody? Pulled rho water G out. What other ones? I can think of maybe one more that we need to use, 2 more. I think we probably need this. And I think we probably need and we need to find we also need delta H is equal to 3 meters. Find what we're after here is the volume of water. All right, so how'd you guys go about solving this puppy? What was your first step? Okay, so SS 1,000 kilograms per meter cubed times 10 meters per second squared times 1 times 10 to the minus 8 meters squared per Newton plus 0.3 times 5 times 10 to the minus 10 meters squared per Newton. All right, what'd you guys get for that? I get, let's see, that's 10 to the 5th, 10 to the minus 3, 5 times 10 to the minus 13. Should be something like 15 times 10 to the minus 14 or something like that. What'd you get? No, it should be 10 to the minus 10. That's a plus. Yeah, it should basically be 10 to the minus 3-ish. 10 to 3, 10 to the 4 minus 10 to the times 10 to the minus 8, 10 to the minus 4. That's what I think it should be. This is all in the noise. Should be roughly equal to 10 to the minus 4. And then let's look at the units here. That is meters squared, seconds squared. We ought to end up with 1 over, let's see, kilogram meters per second squared. That's a Newton. So that cancels out with newtons, and then we have meters cubed and meters squared, so we end up with 1 over meters. Good news. Phew. I didn't make a mistake.
I think that problem we're having is we're getting 9.9 times.
You gotta learn to round. All right. 10 to the minus 4th, roughly. Okay, now what next? Yeah.
And I just made it to where specific storage equals the volume of the water over the area over the difference in the head over.
So you
I just added B that one.
added B to this one.
Yeah.
Hang on, let me think about this. So SS is equal to VW A delta H times B, and then we can solve for VW. I like it. Okay. From equations 2 and 3. A delta H B, which implies VW is equal to SS times A times delta H times B. Reasonable? So 10 to the minus 4th. Area was 10 to the 4th. Delta H was 3 meters. And This is 1/meters. This is meters squared. And B is 10 meters. Okay, that's 10 to the minus fourth times 10 to the fourth. That's 1. So we end up with 3 times 10. So I get 30 meters cubed. Reasonable? Everybody else get something similar? Okay. Can you guess what next question is? Calculate in an unconfined aquifer. Oh, I need to give you a specific yield. What do we measure for coarse sand? I think it was something like 0.2. So, what'd you guys use?
All the same information that the specific storage was for the unconfined aquifer.
So the specific storage, we actually already calculated.
Sorry, look.
So this guy we've already got, right? We got here 10 to the minus 4, because everything that would go into calculating the specific storage would be the exact same.
Isn't the specific yield in there?
Yeah, so first of all, I'm going to say SS is equal to 10 to the minus 4, 1/meters. SY is equal to 0.2. Let's see, we're going to need B is equal to 10 meters. Now the equations, what equations did you use?
Storage equals, the specific yield plus the specific storage.
Times B. So this equation, and then I'm going to use Autumn's combination here. Well, no, I'm also going to use this one. S is equal to VW delta H times A. Right? Okay. So find volume of water. All right. So solution. Find S. So S. Specific yield was 0.2. 10 to the minus fourth times 10. This is 1 over meters, meters. All right, so 10 to the minus fourth times 10, 10 to the minus 3. So S is equal to 0.201. Come on now, that's 0.2. But okay, I'll include it. All right, now, second, find VW. So if we rearrange this one, we get VW is equal to S delta HA. All right. 0.201, 3 meters times 10 to the fourth meters squared. All right, so this is 3,000 times 0.2. Should be like 600. What was it? 6,030. Oh, 10 to the fourth. Yeah, that's 10,000. Yeah, 6,000. Which is basically equal to 6,000. And these are meters cubed. All right. So which one yields more water for a 3-meter drop in head? Unconfined, hugely more. Like so much more that actually the confined release almost nothing. I mean, it's less than, well less than 1%, right? It's like 0.5% of the unconfined water release. Okay, so 2 big take homes. One is that confined aquifers don't have a lot of storage. We'll learn about this later. We'll talk about the mathematics of it. But what that essentially boils down to is anytime you pump a confined aquifer, you affect water levels rapidly. So if a bunch of wells are sharing a confined aquifer, if somebody's pumping, they're definitely affecting the water level in someone else's well. And you don't have to pump a lot of water to affect water levels in those aquifers. But if you're in an unconfined aquifer, there's a lot of water. When you start draining pores, you're releasing a lot of water. All right. So they behave very differently. So this is your first taste at how differently they behave. We can really pump on an unconfined aquifer. We're not going to drop the water level that much. Can't do that in a confined aquifer. All right. Okay. So have a good weekend. I want it known that this is a weekend where you've got no test to study for, you've got no homework. So read your papers once I put them up. And your Mark and Toth, I'll get them up and I want to discuss them on Tuesday. Have a good weekend. Enjoy the snow.
Did you want a summary of those on Tuesday still?
Yes, I'll put the